really interesting popcorn session coming up now. And I think the title says it all, really. The seamless transition from Web3 to Web2 with TEE. So we'll bring up Dr. Zhou, who will come up and speak to us now.
Okay, thank you. Hello, everyone. I'm Shelven from Phala Network, and today I'm going to share some the recent progress on the TEE world and also the Phala Network. Yeah. So yeah, simple introduction. So actually, we have started working on TEE for about 5 years, and now we have a big TEE network all over the world, which is totally come from our community and managed by the blockchain. And but I think the things is changing recently. So I think the most big things recently is that, okay, the many projects, they begin to turn from the previous Intel SGX solution to the system level solution like Intel TDX. So I think the Intel TDX is introduced like 3 important differences here. So the first is the better performance. So like if someone has used Intel SGX previously, you will see that first there is a memory limitation on it, so which is quite tight. I think the largest is just 2 gigabytes memory to use. And actually, if you have used the memory exceeds the 128 megabytes, so the performance will decrease dramatically. But now the memory limitation is totally removed. So, and also previously we need to suffer like about one quarter of the performance overhead using the Intel SGX compared with bare metal. And now these things, I think the performance overhead is negligible now. Yeah. And second, I think, is about the usability. So previously, many of our partners, they have to rewrite their programs to get their running in the SGX. And now, since we have the operating system level support, actually people do not need to change their code anymore. So you just pack the Docker image, and we can get this running inside TEE directly. Yeah. So the third part is about more hardware support. So I think just in the late last year, so the NVIDIA, they have published the first GPU series, the Hopper family, that supports the TEE GPU. I think this is very important because, you know, the GPU is a very important building blocks to running the AI model and also the CK circuit. So I think this also greatly extends the use case for the TEE. Yeah. So first, about performance, there is some more detailed explanation. So actually, this we do not provide this data myself. So the data is from the Intel official, and for the CPU intensive workloads, now the overhead is already below 5%, and for the I/O intensive workloads, the overhead is below 10%. So I think it's quite usable at least from my side. Yeah. So and about the usability part, actually, this is what we are focusing recently. So we provide the TEE SDK called DStack. So the DStack itself is a Flashbots X project. So this means it's jointly supported by Phala and the Flashbots team, but Phala team is the core devs on these things. So it provides some important features. So the first is it supports the Docker containers. For example, I will show you just deploy a Docker compose file and we get it running. And it's equipped with remote attestation reports and also the chain of trust visualization on Web UI. So your customers can easily verify, okay, whether your apps is really running in the TEE. So the third part is that we will automatically generate a domain for your app. And more importantly, since it's a little complex, but generally the certificate itself is directly managed in the TEE. So this means there is a direct end-to-end connection between the TEE hardware and your customers. And actually, they don't even need to know about it because they just type in the URL and okay, now you are connected to the TEE directly. So the fourth thing is that we will decouple the app execution and the state persistency. So this means like, so for example, we allow, we take the root of trust from a single TEE hardware to our KMS, key management services. So this brings a very important feature that, okay, the TE hardware now, they can go down. It's totally okay because the key is managed by our KMS. So when one TE go down, you can just deploy your application to another TE and authorize the KMS to share the key so it can restore the execution. So this help mitigate the service availability problem, which is, I think, it exists for all the TE solutions. Yeah. So this is a demo we just, I think we just done like 2 days ago. So you can see now how to interact with it. So first, the input is just a normal Docker compose file. So here it's a modified Python Jupyter notebook here. Yeah. So so here I want to mention about here. So this is the tab D. So this is a service that's provided by the supervisor. So you can actually, when you try to get the attestation related things, you need to visit this. Yeah. So it's very easy. You just upload the Docker compose file. You click create VM. So then the instance is created. So second, so this is a runnable. Sorry. Okay. So this is the Jupyter notebook. So as I said, you can just get the code, the attestation from the socks directly. So this is the result, the full code. This is from the TDX. Yeah. And so third, actually you can directly go to this URL. You paste the quotes here. Then actually it will tell you whether this is a valid remote attestation report or not. So actually I think we will do better by like explain these attributes to the end users because this is kind of hard for them to understand. But yeah, so this is what we can do now. Yeah, so our general idea here is that we want to make TE hardware replaceable or like disposable. So we do not want to, since the fact is that now all the TE hardware they are manufactured by the centralized manufacturer. So the best we can do is that we ensure we are not tightly coupled to any one of their instance. So we make them replaceable. So yeah, so what we do is, just as I said, we replaced the root of trust. So previously, the root of trust is actually the key which is stored in the hardware of TE during manufacturing, and we replace it with the on-chain governed program. Yeah, So this is how it's generally work. So you can see, so this is the KMS, which is backed by the MPC algorithm, actually, but it's totally governed by the on-chain smart contract. So they specify like what kind of KMS program is valid. Like, so each each MPC node should load. And after that, so this keys is directly distributed to certain TE hardware instance for execution. So this make this part, the underlying part, replaceable. Yeah. So yeah. So actually, I think this also unlock the possibility of like the vendor agnostic TE support. So this means because actually now we have many solutions here. For example, Intel SGX, Intel TDX, AMD SEV, and NVIDIA like TE GPU, and also I think there will future like OpenTE or more. So, but under this design, actually, it's possible for us to support all these implementations. Yeah, given this system. Yeah. So I think this is a very interesting use case for the D-Stack. Yeah. So it's called THE. So it's an AI agent, which is totally controlled by the machine. And this is built by Professor Andrew Miller from the Fastball team, and it's powered by D-Stack. So yeah. And the things I want to explain here, so how is it different from other like AI agents meme coin? So is that I can say it's truly controlled by the machine, in that like you can see every component of these agents, including like the X accounts it's using, and also the email address backed control the X account, and also the AI agent itself, all of them are running inside TE. So unlike others, for example, if I can just run an AI agent, I connect it to the X account and use it to serve the people, but actually I can take back this X account anytime. by submitting my email address. So we have to ensure the whole chain, the whole account chain is controlled by the hardware. So this is what we can do, yeah. Okay, so this is also our research, which is published recently. So the question we will try to answer here is that how usable is TE GPU? Yeah, so we do the experiments on both H100 GPU and H200 GPU. So I would say the result is also very promising. So you can see here the average overhead is less than 9%, which is quite low. So for the AI training part, yeah, this is how the GPU server look like. Yeah. Okay, and so also this is how it works. So still we want the on-chain smart contract to control everything. So here still in the, just like previous pattern, you have to first specify which is the valid program in the smart contract so the TE will load it for you. So then we run the Llama 3 model. Actually, we run, I think, 3 models under different configurations in the TE. One interesting thing about TE GPU is that it cannot operate alone. So the TE GPU must be run with TE CPU together. So yeah, and actually what's happening is that these GPU drivers running inside TE GPU, say they will verify each other to establish a channel, and then the CPU will instruct the GPU to run the task. Yeah. So this is the, sorry, there is something wrong here. It's H200. So H200 has about like 50% more memory compared with H100. Yeah, and also higher bandwidth. Yeah. Okay, I think, yeah, that's all from me. So, yeah, thank you. Let's just connect because I think both the AI and also like other applications are really interested. So if you try to get something related running, yeah, please reach out to me. Yeah, thanks.